Thank you very much. It's a great pleasure to be here. And I'd like to thank our organizers for having me in this session, and welcome everyone, and thanks for joining. My name is Serdar, and I'm a member of the AI Center of Excellence at Fidelity Investments and an adjunct faculty member in the Computer Science Department at Brown. My talk today will be at the intersection of recommender systems and industrial strength open source software. I guess it's fair to say that we all interact with recommender systems on a daily basis. They become quite central in our lives, and they're widely employed in the industry. Classical examples include online shopping sites like Amazon, music and movie services like Netflix and YouTube and Spotify, and even mobile app stores like Google Play and iOS App Store. So the primary goal of these systems is to help users discover interesting content, such as movies to watch, articles to read, or products to buy. And from their perspective, this creates a tailored digital experience. From the business side, it drives new opportunities for us. If you don't really know what goes under the hood in these systems, let me show you a glimpse on how they work. Let's take a look at a classical recommender system and use an illustrative example to see what they do. Here's an imaginary user of a movie recommendation system. Let's call her Jennifer. She's a film aficionado and really enjoyed watching Game of Thrones, The Avengers, and Spider-Man. Next, here are three other cinephiles that also highly rated those three movies. Well, then if you would like to recommend a movie for Jennifer, what we can do is to look at the movies that she didn't watch yet and those three other users liked. For example, the first user likes Batman Begins, James Bond Spectre, and Guardians of Galaxy. The second user also likes James Bond and Guardians of Galaxy, and the third user likes Guardians of Galaxy as well. So as you can see, the Guardians of Galaxy is our top contender here, and it should be the first movie that we should recommend to Jennifer. And notice none of these users liked Walking Dead, so we probably should not show it to her. So in a nutshell, this is how classical recommender systems work. They find similar movies and similar users and connect the two together. These are also referred to as collaborative approaches or collaborative filtering algorithms that build on item-to-item or user-to-user collaboration. The central theme behind this presentation revolves around a single question. The algorithm we just looked at is nice, but notice one thing. We didn't use any other information than movie ratings. So the natural next question people ask themselves is, do movie ratings alone provide enough information to build high-performance recommender systems? And if not, what other information we can use and how can we use that? So if you go back to our example, you might realize that we have many more information about Jennifer herself, and that is the user context. And likewise, we know a lot about these movies themselves, and that is the content features. So when we go beyond these classical recommender systems, we have more advanced algorithms that are content and context aware. So the challenge is how these systems understand and make sense of this enriched content and context information. And that's exactly the topic of my talk today. My goal is to provide you details on content and context-aware recommender systems. This is built on three fundamental parts. The main components are the user context, the content feature, and their historical interaction data. While doing that, we will cover a number of important areas from the broader AI and machine learning literature. And just a disclaimer, this will not be an abstract talk. It will be a practical talk. I'll present usage example from open source libraries. Now, I'm most familiar with libraries that we developed at Fidelity, but what I'd like to emphasize is what's important here is not necessarily one particular implementation, but the main ideas behind them. So we have a long road ahead, and here is what our roadmap looks like. We will start with how to build a representation of the user context. So that was the example in our usage example. That was the information about Jennifer. So here we will study sequential pattern mining and use the sequence to pattern generation library. Once we have the user context, in the next stage, we will look at the other side of the coin on how to build a representation of the content. So these are the movies. Here we are going to turn to natural language processing and use our Textvisor library. So if we bring these two components together, the user context and the content features, we might want to eliminate some redundant attributes or reduce the dimensionality of this aggregated representation. So in step number 3, we will look at feature selection to eliminate redundant features or reduce our dimensionality for efficiency purposes. And we will use our selective library for this purpose. Now, as we're slowly building, once we have our user representation, content representation, what we can do is to combine that with their historical interaction data. And once we do that, we can build machine learning algorithms, recommendation algorithms in particular. And here we are going to use a special form of reinforcement learning called multi-arm bandits to learn from historical engagement data. And for that purpose, we are going to use our Textvisor library. Finally, once we have a system that is running, what remains to be seen is how to evaluate such a system. And this evaluation is both in terms of the performance of the recommendation algorithms, in terms of recommendation metrics, but also, broadly speaking, in terms of algorithmic fairness and bias purposes. To that end, we are going to use our Jurity library. So this is quite a dense roadmap, but one thing worth mentioning is by the end of this talk, my goal is not to build the best recommender system out there. Clearly, that will depend on particular application and particular data sets, but our primary focus will be on fundamental concepts that revolves around those systems. So in that sense, I'm using recommender systems as just a case study. And these algorithms and libraries are useful beyond recommender systems in other applications. In fact, each one of them is standalone and self-contained on its own. So what that means is you can pick up any one of them, employ them in other domains. So here, recommender systems in that sense is just one example application to make these ideas a bit more concrete. So overall, this talk will be successful if you build familiarity with these concepts, quickly evaluate whether they can be beneficial for you in your own use cases, and have a pointer on where to start with practical usage examples. So with that, let's dive in. And before I proceed any further, a big shout out to my team, my internal collaborators at Fidelity Investments and external research collaborators at CMU and Pomona College. All the credit goes to them and our leadership team and the open source team at Fidelity for supporting these initiatives. The work I'm sharing is based on a collection of papers that are published recently and are publicly available. And we share the algorithms from these papers with the broader community in the form of open source libraries. So here I'm giving you a list of open source libraries, which you can find them on github.com/fidelity. Or you could find me on my GitHub account, skadio@github.io, for finding them in one single place. Okay, so with that, let's start with sequential pattern mining. In our movie example, we would like to have a context representation for Jennifer. So to do that, what we are going to do is to search for interesting digital patterns. And then what we can do is to check whether Jennifer exhibits that pattern or that behavior, which can constitute as a vector representation for the user context. So there are a few questions here. How can we find interesting patterns? Do we even know how to define what is interesting in the first place? And in that purpose, we are going to use the sequence to pattern generation library. Okay, so the best way to introduce the problem is to use a simple example. Consider an e-commerce website. For example, we have an ad conversation in an online bookstore. In this scenario, the digital behavior of each user can be captured by a sequence of web pages or books that they are visiting. Now, some of these sequences lead to a positive outcome, such as a book purchase, and others might not. So in this example, I have 6 sequences, and each one of them can have different lengths. And at the end of it, it has a certain outcome, whether purchasing a book or not. But you can imagine that I have millions of such sequences and quite long sequences. So given such data sets, referred to as sequence databases, the main goal of sequential pattern mining is to extract knowledge. For example, if you look at all positive interactions, we can find some interesting patterns. For instance, if a logged in user spends 10 to 25 minutes and opens 30 plus pages, then the probability that they will make a purchase is more than 90%. Now, if we know such an interesting pattern, then we can use this information to increase engagement, make the interaction more engagement, and overall improve the service. Another way to look at this is I can do the same analysis on interactions that lead to negative outcomes and try to find out what exactly are the common patterns in such sequences. So to be precise, this is how it looks like in practice. So in this example, I have 4 sequences here, each corresponding to a user, and they can represent events that follow each other in a sequential manner. The main objective of sequential pattern mining is to find all patterns in similar databases with at least, that occurs at least a minimum number of times. So for instance, in this example, I have a pattern such as ABC, and it's very frequent. It occurs on every row. So every customer exhibits this behavior. Another interesting pattern is the CB pattern, C followed by B, and this pattern occurs in 3 rows, 3 users. And the goal is to find all such interactions that satisfies a minimum threshold. So now, wouldn't it be nice to have a software that automatically extracts such patterns from sequence databases, such as clickstream behavior that we looked at in the bookstore example? And this is where the sequence to pattern generation library comes into picture. This is a decision support system for sequential pattern mining, and I'll walk you through the example a little bit. So in this case, I have a sequence database similar to the example we looked at. I have 3 sequences here, and I can create a sequence to pattern object based on my database. Now, what I can do is to also construct attributes that corresponds to these events. For instance, I might know the price attribute of every book or every advertisement on each event. What that enables me to do is I can add semantic relationships. For instance, I can say I want patterns that have an average price between 3 and 4. And I want sequences that happens at least on 2 rows with minimum frequency equals to 2. So that's where the idea of interesting patterns comes. So what you can do is to add constraints on attributes, and these can have different relationships such as average or median or a span constraint or a gap constraint. I will refer to the papers for details on how these constraints work. It can work with the numerical or textual databases. And under the hood, this is implemented in Cython with an efficient C++ backend and a high-level Python API, as you see here, that can mine millions of events within minutes. So this library is available and off-the-shelf, readily available for anyone to use and to mine sequential patterns. Okay, and this concludes the first part of my of our roadmap. So in step number 1, we built the user context. Now let's turn our attention to content features and switch gears to natural language processing. In this section, we're going to look at text featureization and in particular our Textvisor library. So taking a step back, how to make sense out of language has been a challenging question for AI. And recent major breakthroughs in machine learning came from the applications of deep learning architectures on natural language processing, most recently the transformer architecture. So as humans, we understand language and we understand text, but machines don't. So we have to featureize text into numerical vectors and exploit the geometry in this new space. This process is known as creating an embedding. Essentially, the high-level idea is simple. You take a word and map it into a vector in this new space. Here's a famous example that you might have already seen. If you look at the relationship between the king and the queen, it is similar to the relationship between man and woman. In fact, if you take the number or the vector that corresponds to the king and subtract man, and add to that vector the word embedding of woman, guess what number you would get? You get the number representation that corresponds to the queen. So no human went in there to write down that logic, but the machine automatically inferred some semantic information on its own. So this is pretty cool. And today NLP has reached a level where it can reason about semantics behind language just like we do. And this is what's behind Siri on our mobile phones and Alexa, and that's how they understand us. So the same idea applies to verbs, tenses, and just any relationship between arbitrary objects such as countries and capitals. For instance, the relationship between Turkey and Ankara is similar to Germany and Berlin. Now you can build some question answering systems that can come up with answers on its own. So the recent developments in the open source NLP community provided us with a set of rich tools. Popular examples include NLPK, GenSim, Spacey, more recently NLP, Flare, and my favorite, Hugging Face Transformers. And thankfully, most of these libraries come with pre-trained models, which speeds up application development. But still, the availability of various techniques in standalone isolated libraries doesn't immediately provide a solution for us. We need to work with different tools, build a custom layer on top to experiment with the best text embedding method of our choice. And under the hood, these libraries have different input-output specs. Some work with a numeric NumPy array, some work with a sparse matrix, some work with a PyTorch tensor, list of floats, and so on. And this is a work that everyone has to do from scratch, and it is detrimental to reproducibility and fast, rapid experimentation. So to combat with this challenge, we wanted to create a unified view of representing text embedding methods and accelerate the usage of these embeddings by practitioners. So to do that, what we did is to introduce a context-free grammar to represent the unification of text featureization. So on the left, you can see this grammar. I on purpose put this in small letters because I don't want you to read the production rules in this grammar. But the idea is that it gives us a principled way to bring these components together. And the formula is quite neat. Textvisor equals embedding plus 0 or more transformations. So you take an embedding, and on top of that, you can apply a transformation, meaning some dimensionality reduction. In terms of embedding, there's more than 25 plus embeddings in there, anything from GPT-2 to Transformer XL and BERT-like models. And in terms of transformation, we have LDA, NMF, and a number of other transformation methods in that. So you can combine these together. And in fact, you can build arbitrarily complex ones by concatenating these different embedding plus transformation combinations one after the other. And this is how it looks like in practice. So here is a Textvisor library. So I'm using a very simple embedding here called a term frequency inverse document frequency, TF-IDF, which is basically a counting based operator. So it counts the frequency of different terms in the text. And I can have this embedding. I have a document consists of different strings, and I can transform my documents into the vectors. So this is the king-queen example that I showed you. Now, this is a simple embedding. What you can do is to take this embedding and wrap it with one or more transformations. So here I'm applying a non-negative matrix factorization on top, and I'm applying a single value decomposition and SPD algorithm. I'll skip what these algorithms do, but the idea is that by just changing that embedding space, now I have a different vector representation. And you can do interesting things like even a BERT-like model That depends on word embeddings, which you can pool using the minimum of the words in a document and so on. But essentially, the API is unified thanks to our grammar representation that gives us a systematic way to explore these different embedding space. You can read more in our paper from AAAI, and here is the link to the library. Okay, step number 3. In the first 2 sections, we were slowly building our state and context representation, which consisted of the user information and the text information on items. As an optional exercise, what we can do is to perform a feature selection on top of this representation. The main goal would be to eliminate redundant and correlated features. For that purpose, we are going to use the selective library. So what we did so far is in the first part, in step number 1, we built user features from sequential, maybe their digital activity. And in the second part, we used NLP to build content features from text input, which gives us in combined a context representation, right? We can combine this with historical engagement data. So whether this user liked, maybe this is a positive reward, maybe watched a movie or liked something with this item, with this movie. And maybe another user with another movie and so on. So we can bring these context representations together with historical engagement. So one thing to realize is there's a trade-off here. So the number of features, so each time I'm adding a column, that is an implication of how many observations I need to add to my training data so that I can reasonably train for such a system. And there's another trade-off, which is size and runtime. So the more data set, the more columns I have, the more rows I need, the bigger the data set, the longer the processing will take. So what you might want to do is to do some feature selection. I'll give you a quick summary of what feature selection techniques might look like at a high level. But the main idea is feature selection can be performed in a supervised or unsupervised fashion. When I mean supervised, the previous example I had where I combined the reward labels was a supervised data set because I knew that this user and this item led to a positive engagement. So I had a supervised observation with a truth label attached to it. If I didn't have that, then I would have an unsupervised machine learning task. You can do feature selection in supervised or unsupervised fashion. The simplest thing you can do is to look at individual features. So I can look at single columns. And the most extreme case is that this column will have absolutely no variance, which means it's not even a variable, it's basically a constant. And I don't need that column in my data set because it's not informative, right? So if I don't see much variance between different observations, I can drop this column. So the simplest thing you can do is to look at the features of individual columns. A step beyond that, what you could do is you can take pairs of columns, pairs of features, and look at their pairwise correlation. Now, what that correlation is can depend on different methods. So you can use something like a Pearson correlation or Kendall or Spearman correlation. I'll not go into details of those, but essentially they will tell you if 2 things are very, very similar to each other, maybe you can drop one of them, okay? Now, switching to the supervised case where I have these ground truth labels, the reward information, what I can do is I can again look at these individual columns and try to attach or make a relationship between this feature and the rewards that I observe. So maybe I can run an analysis of variance like an F-test or another statistical test like chi-square or mutual information between these 2 data sets and decide whether there is any link or any information that I can use between the 2. If not, then I can probably drop this feature because there's nothing to do with the case that I'm interested in. And extend this a step further, what you could do is now you can take more than one column, so you can look at multiple features together and in fact try to build a model that takes this representation and tries to map it to the 0, 1, the binary outcomes that you see. So you can build a linear model and the coefficients of this linear model can tell you like how important these features are in predicting the label. And you could say that I'm going to take the most important ones. Or you could build a nonlinear model or a tree-based model, which again tells you feature importance that you can use to decide which features you want to keep and which features to eliminate. Okay, and to do that, now you have the selective library. This is how it looks like in practice. So the methods I mentioned earlier can be seen as variance-based methods where you can set up a threshold to drop columns below with that variance value, or you can look at the correlation and define what exactly you mean. Maybe it's Pearson correlation, or look at statistical significance of the features and the reward label, and maybe say that I'm going to keep the top 3 features. Or you could build a linear model and use the coefficients of these variables as the importance, and again, keep some top K, or even build a nonlinear tree-based method and again, prioritize a number of them. This is the data and label, which is in my slides that corresponds to the reward column and the data matrix. And you create a selector with any of these methods in there. And what you do is you fit transform your data set, and you would get back a subset of the data. Okay. Now, this is the part that's where the magic happens. Now that we have our data set in place, what we can do is build a machine learning algorithm. So far, we were building our data set progressively by adding user information, content information, maybe cleaning that data set a little bit to eliminate the redundant or arbitrary features. We combined it with historical engagement data. So we now have a data and a label at hand. And what remains to be seen is to build a machine learning model to make recommendations. In this case, we are going to use a multi-unbanded algorithm and our Textvisor library. So let me open a parenthesis here and talk a little bit about background on multi-unbanded algorithms. I'll give you an example so that you can relate to this setup. In daily life, we frequently face situations in which we must choose between known and familiar entities and lesser known or unfamiliar ones. For example, let's say you are in a restaurant and you're ordering from the menu. Do you go with your favorite dish, or do you try out the chef's daily special? So the choice between these different options, the situation or our mood at the restaurant at that day, which is the context that we are currently. Upon making a choice using maybe some specific learning policy, what happens is we observe reward. So we order something, we like it or we don't like it. And then there's a feedback loop that updates our expectations about these decisions so that we can make the next decisions. So these problems are typically referred to as online sequential discrete decision-making problems. And one way to address them is to use multi-unbanded algorithms. The important bit here is that on each turn, when you're making a decision, we are facing a dilemma. We can choose an arm, we can make a decision with the highest average reward. We can pick the dish that we like the most and receive an expected reward. So we're kind of like in the exploitation mode. Or we can choose an arm or make a decision for which we don't have enough information or much information yet, but potentially learn something new, which is an exploration mode. So overall, the idea behind these multi-unbanded algorithms is to balance this exploration-exploitation trade-off in order to maximize the long-term cumulative rewards if you keep making these sequential decisions one after the other. Here is a really nice survey on contextual multi-unbanded algorithms if you want to learn more about these different techniques. And in fact, these algorithms are quite well known in the industry and used in a number of applications. I present you with a few here, for instance, in advertisement optimization or news article recommendation. In this case, it's Yahoo who deployed bandit-based algorithms for news article recommendation. It's also used in healthcare for clinical trials, or even for hyperparameter tuning of machine learning algorithms, as in the case for Yelp's optimization engine. And my favorite example from the Netflix group on movie artwork personalization, in which they actually decide which poster to present for a specific movie depending on the user themselves. So for the same movie, we might actually see a different artwork. Okay, so at the time when we were studying these algorithms, there were not many options to use multi-unbanded algorithms in native Python tech stack. And in order to fill this gap, we built Mapvisor. And here's how it looks like. I'll walk you through this case. Let's go back to our movie recommendation example users with movie number one again, movie number two, number of minutes, or they followed this movie, maybe 20, 17, 25. So I have arms, decisions, and rewards. Remember, each decision is made under some particular context. And connecting this back to what we did so far, the context is nothing but what we know about the user and what we know about the movies. So we can use sequential pattern mining to generate user context. We can use NLP and texturization to generate the item context. We can bring them together. Under this context, I make a decision of the two options I have, and this is the reward I observe. So I can pick a particular learning policy. So what to make out of these observations from historical data sets. So here I'm using an upper confidence bound. I won't go into details what this algorithm does, but there are different ways that you can learn from this past experience. In fact, there are 8 different learning policies and 5 different neighborhood policies that we can combine together in Mapvisor. So you could have changed these parameters and add a neighborhood policy as well. But regardless, given a Mapvisor model, what we can do is fit these decisions. So I made these decisions under this context, and this is the rewards that I observe. Now, the interesting bit is when you observe a next context, when the next user arrives, you know their content, you know their context representation, and you can ask your banded algorithm to make a prediction based on the learning process that it learned from the historical data to make the next recommendation. And for that next recommendation, you're going to observe a reward, and then you can fit this again on your model, put these expectations back into the learning policy to update your expectation and continue making decisions. So this has a very nice online nature that can adapt to the data sets and the streaming in style. You can read more in our papers, and the link to the library is here, or Mapvisor. And finally, what remains to be seen is performance evaluation. And not just performance evaluation, but also a fairness lens and a fairness algorithmic fairness evaluation, as well as if there is unwanted bias, we need to be able to do some bias mitigation. We want to look at specific recommendation metrics. And in order to do that, we're going to use our Fidelity library. So I'm gonna walk you through these examples. In this case, I have an actual data set, which refers to the rewards label that we have seen before. So I know that the first user looked at the first item and maybe they clicked on it, or maybe they didn't click on it. So this is what I see in the data set. So these are my true observations. And let's say I have a model like the map model, the Mapvisor model, or maybe any machine learning algorithm really to make that prediction. And for this user and for this item, I make some decision. Maybe I have a click probability and turn that into a recommendation if the click probability is high, and so on. What I can do then is, if I have these truth labels and some predictions from a machine learning model, I can look at recommendation specific metrics. The simplest or the first one that comes into mind is click-through rate, the CTR. So it's literally based on how many clicks what my machine learning algorithm is going to get if I follow its recommendations. But there are also other recommender specific metrics that are interesting. For instance, the normalized cumulative gains, which actually looks at the ranking nature of these algorithms. For instance, if you're making more than one recommendation, there's a difference between getting a click in the first position versus a third position versus a fifth position. So you can try to normalize that click behavior if you're like thinking about a search where you have a ranking and there's a difference between the first click that you will receive and the clicks that come after that. There's also different scenarios. So if you have a K parameter that decides how many recommendations to make, so if you make 1 recommendations, you're talking about K equals 1, but you might also recommend in an article recommendation might present the user with 4 or 5 different articles. So you have a top K recommender system. And then what you can do is to analyze your algorithm and how its performance changes for varying Ks. So what does it do for the first prediction? How does it look like if I generate a top K recommendation and so on? So then you will introduce concepts like precision, recall, and average precision. So what's my average precision as K iterates? And you can generate all these metrics and feed in your actuals, the truth, which is basically your data set that you observed historically, and what your model says that it would do. And then you can look at the different recommendation metrics and evaluate the best algorithm for your case. So these are recommendation-specific algorithms. Let's look at the case for fairness evaluation. So fairness is quite a complex field. Here I'm talking about algorithmic fairness as defined by several different metrics that exist in the literature with no consensus on what is a standard or the best fairness metric. But what you can do is to consider a series of them so that you can evaluate your algorithms accordingly. In this case, I have a binary fairness metric called statistical parity. And what it does is if you have a membership in your data set, so for each of the users, maybe you know some information about an unprivileged class. So what you might want to be interested in is statistical parity, which basically tells the users in the unprivileged class should be just as likely to receive a positive treatment or a positive prediction as the people in the privileged class. And this test uses the difference in these positive prediction ratios. And in this case, I can create the statistical parity metric. And what I would need is this membership information. So I have my predictions, binary predictions from a model, and I have this privileged or protected class membership attribute on my users. Zeros and ones can refer to your definition of what is a protected class is. It might be based on age, for instance, or marital status, and so on. And then you can actually ask, what is my statistical parity score if my model makes these predictions with these protected class attributes? Now you can extend this case beyond binary predictions. So maybe your algorithm is not making 0-1 decisions. So it's not just movie 1 and movie 2, but we have multiple choices like A, B, C. So you have multiple classes, and that would also work. So you add that information and you can again ask, what is my, this time you will have a multi-class fairness metric for statistical parity, or even you can have multi-class and multi-label. So my algorithm has to deal with multiple classes, but it doesn't make a single decision. So as in recommender systems, we are interested in top K. So at each step, you might make multiple label predictions. So I'm predicting A and B, so maybe that's a top 2 recommendation. And finally, if let's say in the worst case, we have some unwanted bias, what we can do then is to, for instance, use a technique like equalized odds for bias mitigation. And what would that method going to do for us is that we can look at not only the predictions of the model, by the likelihoods that it generates. And then given this protected attribute information, the equalized odds basically tells us that it's going to try to change the likelihood of these models in such a way that it's not going to hurt the performance of the model, but it's going to equalize the odds between the protected and unprotected group, so that our likelihood or our odds of positive treatment for both cases are indistinguishable from each other. So if we do that, we were going to end up with some fair predictions and fair likelihoods, which are going to be perturbations of the model's decisions, in which it will allow us to mitigate the bias, the unwanted bias. So you can read more in our paper and in our library in Jurity. In practice, you also have issues such as sometimes you don't have truth labels in some data sets. That's a common issue in practical scenarios in the industry. And we study these considerations in our publications. Okay, so let me finish where we started. We looked at the user context using pattern mining. We looked at content features using NLP. We looked at feature selection. We built bandit-based recommendation algorithms, and I showed you how to evaluate such models. So overall, if you bring these, yes?
Sorry to interrupt. We have 5 minutes remaining.
That's fantastic. I'm just about to conclude. So this is my last slide. Overall, if we actually bring all these components together, we can build an entire machinery revolving around recommender systems. At the heart of it, we have the bandit algorithms that operates on user profiles and content features. But beyond recommender systems, I guess what I tried to do in this talk is to cover important concepts in machine learning, such as natural language processing, pattern mining, fairness evaluation, and feature selection. Feel free to start these repos and use these libraries, and we'll be happy to hear your feedback. And I hope these would become helpful in your own applications. Thank you very much.